This is case study the EWI upgrade, Earth, Wind and Fire integrated. EWI is a high-rise building on the campus of the Technical University in Delft. It is next to the well-known Nieuwe Kerk, a beacon in the landscape of Delft. EWI is designed and constructed in the end of the 50s and begin 60s. It is an architectural sign of functionalism and efficiency and was progressive in its use of prefabricated materials. The building consists of stacked office spaces and laboratories to reach 90 meters in height, where radio antennas are deployed to be used for scientific research. Nowadays, more than 50 years after its construction began, the EWI building is considered to be outdated, not necessarily because of its architecture, but because of different rules and regulations regarding the climate performance of the building. Climate-wise, detailing is poorly designed. Single glazing is used for the whole facade. In the 60s, the architects invented a system to regulate the interior climate. By creating a second skin on the two widest sides, air in the cavity is preheated by solar radiation and functions as a buffer between in and outside. Every floor has its own system, which consists of 4 different electrically powered ventilation units. Despite the fact the architects of the building invested a lot of effort in designing an appropriate climate system, it is nowadays considered to be very inefficient and energy consuming. EWI can use a climatological upgrade. This is Bronsema, a professor of the TU Delft specialized in the field of climatization of buildings. He developed an integrated system consisting of 3 different components: a climate cascade, a solar chimney and a Venturi roof, which all work together to become a green and naturally powered air conditioning system. It functions as follows. Wind is blowing into the so-called overpressure room and is leaded into the climate cascade, which in wintertime preheats the air and in summer cools the air by using water of the necessary temperature, which is stored in an aquifer. The pre-cooled and preheated air is led into the usable spaces. On the other side of the space, the air is sucked out by an underpressure developed by its solar chimney. The absorber in the chimney gains a lot of energy by solar radiation, which heats up the surrounding air quickly. This air rises and exchanges its energy by the use of a fine wire heat exchanger and is leaded again into the aquifer. Additional suction of the air in the solar chimney is provided by the 3rd component, the Venturi roof. Wind comes from the left side, and while moving through the Venturi it speeds up, causing an underpressure in the narrowest part, which is connected to the solar chimney, and keeps the air moving through the whole building. When implemented in the EWI building, this system will improve the climate and energy consuming conditions drastically, but the focal point of this exercise is on one component. Let's take a look again at the characteristics of the direct surrounding of EWI. EWI is known for its hard winds, causing trouble for cyclists and pedestrians. The relationship between EWI and the wind is interesting as a starting point for further investigation. What follows is an examination of the necessary conditions for the Venturi roof to function adequately. First, it is important to understand that wind speed is increasing linear by an increase in height, which is shown in this graph. On the horizontal axis is the wind speed, on the vertical axis the height. Then we add 2 constants and we draw a line in between. EWI is 90 meters high, one of the highest points in Delft, which means the wind speed reaches high values on top of the building. Next is a graph of the average wind intensity in Delft for different directions. It becomes clear there is an average predominant wind direction, which is the southwest. EWI is a rectangular shaped building with a length of 80 meters and a width of 17 meters. This graph shows an increase in length of the Venturi will increase the efficiency of its functioning. A lower pressure in the throat of the Venturi has more suction as a result and causes the system to function better. The examined characteristics of the EWI building are resulting in good conditions to use a Venturi roof, but can this component add something to the building except a better functioning climate system? This is the starting point for the EWI upgrade. There are 2 points of departure. 1. Making use of the good panoramic views on top of the building, and 2. Increasing the fact EWI building is a beacon in the landscape.